Telegrapher's equations in frequency domain. So we've seen how we can start to approach what we call the Telegrapher's equations and how we can simplify them in different terms. Now what we want to describe is actually the whole function, so voltage and current over time as well as space. And what we assume now is that we have a sine or cosine wave. So the dependence of voltage and current on time and space takes a form of a harmonic wave, a time harmonic function. Now when we do that, we can describe the whole function in terms of a frequency, so one frequency if we just have one main function. And this then holds true for every point in the transmission line. And by using complex terms, we can solve the equations, the wave equations in the frequency domain. And by implementing Fourier transformations, we can provide solutions for almost arbitrary time sequence. Okay, so what we do now is, instead of writing sine and cosine functions, which are not easy to handle or not quite as easy to handle, we go to an exponential function because it's much easier. The advantage is when we do our differentiations, as we have to do a lot, you've seen that in the Telegrapher's equations, they reproduce themselves, so it's much easier to use them. Also, it's a bit shorter. Okay, so we ended up at the point where we wanted to write our voltage as a function of space. So we're solving a one-dimensional problem, and what we take is now the form of the amplitude times the complex expression with a phasor. So I would write that down now. We have here the amplitude term in the beginning, and then in the back we have the phase information. Just as a reminder, when you think of these waves, it's always a sine wave. I will write down Euler's equation just as a reminder how we transfer the exponential form into cosine and sine waves in the complex form. Here is with x, just as an example. Okay, so when we want to know the voltage at a specific space and time, what we do is we take the real part of now the voltage at z times the phase information times then we take this apart and we take the phase out. So I omega t is the complex wave, so we have the wave and the amplitude here. The important point is that the magnitude part always gives us the magnitude, as its name is, and the argument in the phase gives us the difference to a selected phase at a specific space position. But we can just choose the reference position to be at the time t equals 0, and then we can simplify the whole thing. Okay, now we'll write that down here again as a cosine form, just as a reminder for later visualization. Okay, so what we do now is we take our exponential expressions for voltage and current. And this is just taking all the same equations again and putting them in. So let's start with the voltage. We will make what's called an Ansatz, so an approach. The voltage comes first. And second, we take the current. And again, just with the exponential wave function. And now what we need to do is we take the Telegrapher's equations we had before, so our transmission line equations, I would just abbreviate them here, but not the ones we know. We transfer them now to the frequency domain, so in frequency domain. And when we look at that, you will see that we can just rewrite that we take the second derivative in space as we always had with our standard equations. That's just as we had it above. So the second space derivative of the voltage equals L prime C prime times, and now we put the exponential approach in, which brings us I omega squared times U plus, and then we go with the rest. R prime C prime plus G prime L prime times I omega U, which comes from the first time derivative, and then we have G prime R prime U. So now we got more or less rid of the time derivation, and of course this will be the same equation, so analog in current. Okay, now we can rewrite that a bit, since we got rid of these nice time derivatives, and this will then look like this. The left-hand side stays as it is, but on the right-hand side we get the following expression, which is R prime plus I omega L prime, and then times G prime plus I omega C prime, and the voltage. Now we will rewrite that a bit, because we can identify something here. And we will take the whole part in front of the U and call that gamma squared. So this is just a naming convention, but the way we put that now, we can call that the propagation constant, because you see that it will summarize how the wave is propagating within one term. Okay, propagation constant, I write that down here. Now the good thing is we can separate that again for a real, so an amplitude and a phasor part, like we did in the very beginning for our first complex wave approach, and then we can kind of identify the terms together. So if we compare that now, just write down what gamma actually is here. So if we put that together, we get gamma equals the square root and then all what we have right there. And now with these equations, we can take the next step and understand what is an impedance. But this is already our first important result here. Now we have a propagation constant that we can calculate, and that will give us all the information, or most of the important information, before we even start. So that was it for this part. Just go back a second and have a look. We have our description here, and we identify the propagation constant that separates the real and the imaginary part, again based on the properties that are resistance, capacitance, and inductance per unit length. And we can now go into the part where we will calculate the main parameter that identifies a transmission line, which is the impedance.